Welcome to the last day, the first session of the last day. Thanks for braving the early morning and the cold temperatures, I guess. Okay, so this is probably my favorite session in this conference. So the first paper is in this line of recent work that provides extremely strong, actually tight trade-offs between the amount of memory that it needs to learn a concept. So to go like slightly higher level, so providing trade-offs between the amount of memory an algorithm uses and the time it takes to run. So this is a very, very hard problem. People have been looking at this in the cell probe model for a while, and in general, those questions are extremely hard. And people are thrilled if you prove sort of anything. So in this kind of recent line of work where people are looking at learning problems, trying to get trade-offs between the amount of memory and the number of samples it requires, we've had a lot more success in this line. So what's the difference between them? Well, basically in these settings, people are analyzing learning algorithms. And so there's some distribution over inputs. And you're analyzing an algorithm that gets samples from these distributions, has a limited memory, and is trying to learn something. So what's the difference between these? Well, in a nutshell, basically, because of the distributional nature of the problems, these are now kind of information theorems. Limited memory, you're getting information, but to get more information, you need to compress things. Now it's kind of an information problem. And in some sense, algorithms, computer science is hard, information theory is doable. In that, there's no black hole of P% P at the core of information theory. And anyway, so that's kind of led to all this really exciting recent work, so the stuff of Ron Roz, and earlier paper of both of you. So there's been a couple of recent papers along these lines. This paper also proves tight bounds, although the approach is quite different from the Ron Roz style approach. And with this kind of exciting new area, it's nice to have as many different different understandings, different proofs as possible. And this approach is really nice, and it's something that I think there are some connections that might come out of this that aren't accessible via Ron Roz style proof. I'm really excited about this. The next paper, pseudo-random generators for low sensitivity functions. So without trust that, I trust that you'll define sensitivity conjecture. Basically, if you have a Boolean function, the sensitivity tells you sort of how many input variables you need to flip to change the value of the function. And for the sensitivity conjecture says, if you have a low sensitivity function, then it can be represented by low degree polynomials, low depth decision trees, and so on. And recently there's been a bit of work in the direction of saying, well, we can't quite prove the sensitivity conjecture. What else could we hope to say about low sensitivity functions? And in that sort of line, so this paper gives pseudo-random generators for low sensitivity functions. One thing which is kind of cool about this is if you were to assume the sensitivity conjecture, that would imply that maybe possibly even better pseudo-random generators would exist. So in some sense, this is kind of like a necessary stepping stone, a necessary intermediate point in proving the sensitivity conjecture. So that's cool. The next paper, this learning by refuting. So here the authors propose this computational analog of Rademacher complexity, which captures the sample complexity of efficient agnostic learning. So I guess those of you who know, Salil is somewhere in the audience, so those of you who know Salil Vedant's paper, this is sort of a complement to that. So Salil has a sort of analog of this for proper learning where there's no noise, and this is sort of a complement of that in the case of agnostic learning. and this also fits nicely within the recent sort of line of work from Amit Danieli and his co-authors, which are trying to prove, hardness for learning problems via reductions to reductions to whichever way it is to refutation problems. Okay, and then there's this last paper, which this is one of my favorite papers. Seemed super different, and I really, I'll make a fool out of myself if I try to explain what's going on here. So hopefully Greg will clarify this. But it's, yeah, anyway, it's, be ready for something crazy.